Does the following set of vectors form a basis in three-dimensional space? So we're given this set of vectors 1, 0, 0, 2, 2, 0, and 3, 3, 3, and we're trying to figure out whether this set forms a basis in the three-dimensional space or not. Okay, so we know that in order to show that the given set of vectors form a basis, we need to satisfy two conditions. Okay, the first condition being that vectors must be linearly independent and the second condition is that vectors must span the three-dimensional space. Okay, so in order to show that vectors are linearly independent, we need to have that v1 stands for the first vector here with the three components 1, 0, 0 multiplied by the scalar k, in this case k1, because that's going to be applicable to the first vector, right? Vector 1, which is the scalar k1, right? So k1 times v1 plus k2 times the second vector 2, 2, 0 plus k3. So all these scalars are different scalars, right? They must be different, they must be unique, distinct, right? k3 times the third vector here 3, 3, 3 is equal to the 0 vector. All right, and we have to have that the system only contains the trivial solution. Okay, this will show us that indeed the vectors will be linearly independent. Okay, and we also know that the 0 vector is basically 0, 0, 0, because we're talking about three dimensions here, right? Three-dimensional space. Each vector having three components. And so the 0 vector must have three components, all of them are zeros. Now the second condition is that the left side stays the same, right? Because now we want to make sure that the vectors span the three-dimensional space. And so k2 v2 plus k3 v3 is equal to the b vector. Okay? And the b vector is not going to be a 0 vector, right? In this case, b vector is going to be broken down to the same three components. It's going to be b1, b2, and b3. Okay, so let's see. So now, what does the first equation tell us? We can actually formulate a system of linear equations by using the first condition equation that we've developed, right? The vector equation, right? So the first condition vector equation means that we will have k1 multiplied by the three components here, right? So so first we will take care of the first component in each vector, and we're gonna have three equations, right? Because we have three components in each vector, it calls for three equations. The first equation will deal with scalars multiplied to the first component in each of these vectors, right? And then added together those products, right? So k1 times 1 in this case stays k1 plus k2 times 2, the first component of the second vector, right? k2 times v2, right? Which is going to be 2 k2 plus the first component of the third vector 3 times k3 is equal to what? 0, right? Because we're talking about this vector equation, we have to have the right side 0 all the time, right? The next thing, we're going to take k1 and then we're going to multiply now k1 with the second component, right? So we're going to be dealing with second component now for the second equation on the left side. Second component in each vector is multiplying their respective scalars, right? So 0 times k1 is 0, so we don't have to write that down. Plus, we don't have to write the plus yet. 0 times the second, k2 times the second component, so that gives you 2k2 plus. Now the second component in the last vector is 3, right? And we have k3 multiplying that, right? So 3k3 is equal to 0. Okay, so now we're going to be dealing with the third component finally, accounting for the last third equation, right? So 0 times k1 is just 0, we don't have to write it down. 0 times k2 is still 0, so we don't have to write it down. 3 times scalar k3 is giving you non-zero, right? 3k3 is equal to 0. Beautiful. So now we have three equations. So the same left side applies to this vector equation that we're going to test for spanning, right? k1 plus 2k2 plus 3k3 is equal to b1, 2k2 plus 3k3 is equal to b2, and then 3k3 is equal to b3. So now instead of solving each equation and finding whether, satisfying both conditions separately, you can actually kill two birds with one stone, right? You can actually form a matrix A, right, the coefficient matrix that is, by using the left side of the system of equations here. And coefficient matrix obviously means not an augmented matrix, so you're not going to include the zeros. You're going to include only the left side coefficients for each scalar, right? So in the first equation you have 1, 2, and 3. In the second equation you have 0, 2, and 3. In the third equation you have 0, 0, and 3. 0, 0, 3. So all it remains now to show is that if the determinant of this matrix, coefficient matrix A, is not equal to 0, then you will have satisfied both of these conditions successfully. You're killing two birds with one stone by finding out whether the determinant of the coefficient matrix is non-zero, right? If it's not zero, you satisfy both these conditions. Vectors are linearly independent and they are spanning the three-dimensional space, which means that the given set of vectors does form a basis in the three-dimensional space, right? So let's solve for the determinant. That should be easy, right? So the determinant of A, coefficient matrix A, is going to be taking this. So we're going to work with the master numbers here, right? What I mean by the master is that 1 will multiply 1 will stay there, and then what you're going to do is you're going to eliminate the first. You should know how to do this already, but let me just refresh your memory. So 1 means that you will disregard the first column numbers and the first row numbers, right? So 1, and then you're going to be working with these two, which are neither part of the first column or the nor the first row, right? 2, 0, 3, 3. 2 times 3 minus 3 times 0. Right? These four numbers, 3 times 0. So treat this as a determinant that you're trying to find of a 2 by 2 matrix. Suppose this is a 2 by 2 matrix. The determinant of this would be 2 times 3 minus 3 times 0, right? 3 times 0. So now, remember that there's a negative sign applying to this. So you're going to have minus, you're going to subtract the second master number, and again, why is it master? Because you're eliminating now inside this part here, inside these brackets, you're going to eliminate the respective column number of the two, which is 2, the second column, and the first row, right? So no numbers that are in the second column or the first row will be inside the bracket, right? It will be the numbers outside of these two, right? These are the constraints. So 0 times, so treat these numbers 0, 0 and 3, 3 as numbers in a 2 by 2 matrix, right? So the determinant would be 0 times 3 minus 3 times 0, right? And finally there's a plus sign again, just like in the first, for the first number, right? You have alternating signs, right? So plus 3, now the master number 3 eliminates that column and that row, right? So now this is easier to see, right? Just like in this example. because the numbers are clumped together, which is great. So treat it as a 2 by 2 matrix. So the determinant would be 0 times 0, the main diagonal, minus the opposite diagonal product, right? 2 times 0. So now you didn't actually have to do all this work, but unless you see it beforehand, you should still do the work. And why do I say it's obvious that you didn't have to do so much work? Is because you have zeros here. So this whole thing is 0, and so is this, because of all the zeros, right? So the only thing that is non-zero, and when I say non-zero, I'm already leading you to the point that the determinant is not going to be 0, right? So that's going to be what? That's going to be 1 times, and this is 6, and this thing is 0, right? So it's just 6, right? So 6, and look what it means. This is not equal to 0, so the determinant is non-zero. So guess what you just did? You satisfied both of these two conditions, right? So you can say 2 conditions. I should probably just say conditions 1 and 2 are satisfied. So what does it mean? It means that the vectors are linearly independent and the vectors also span the three-dimensional space. So what does that all mean? Since the conditions are satisfied, it means that the given set of vectors forms a basis. Forms a basis. I hope this was helpful. Thanks for watching, and see you in the next videos.